You can hear me again now, right? Okay. I think that was the problem. It looks like when I connected in with this USB-C cable, it went to this Realtek audio, which I'm guessing was never plugged in. So, all right. Well, we're kicking now, so we'll have to remember that for next time if it doesn't default to it. Okay, so let's see where we left off. Oh, okay, here we go. Ugh. Well, for starters, I had mentioned last class that you're going to be working on some stuff through the Canvas course while I'm covering some background information here in class. So for the first week, um, uh, for the first week of class, if you've gone and looked at Canvas, it has you write like a stupid little program to like read something in, you can print it out. There's a link to the textbook. The textbook's a free book online as you read like the first two sections that introduce you to that stuff. So it's getting you just to play around with Google Colab and that kind of stuff. So I think that's due Sunday at midnight or something like that. So make sure you look at that up on Canvas. Shouldn't take real long, just kind of as introducing you to the tools while I'm playing catch up with the background information. Questions about that?
You taking notes on it?
Well, you do whatever you want, I guess. Um, I mean, I don't think you'll need notes for it because we haven't covered the stuff that you'll use for it, but it's 2 lines of code. Here we'll even put it up on the video here. That's the assignment right here. Enter a message, read it in, store it in a variable, print a couple things. That's the assignment. So it gets you used to typing some, code in and stuff like that, just to get used to the tools. All right. So I want to get back to this. All right. What's a CPU? So let's ask the proverbial question and get the proverbial wrong answer. What's the CPU? What can you tell me about the CPU? Okay. So central processing unit, what does that mean? Go ahead. Okay, what does that mean?
Processes all the like computer functions and sort of like pretty much just like what he said, the brain. Like without your brain, you can't really think, can't really like walk and stuff.
Okay. So our brain makes things happen, right? So if everybody puts their hands up, wiggle your thumb like that. Everybody can do that, right? Here, online people. Wiggle their thumb like that. Everybody can move their hand like that. Now, those are really impressive things, right? If all you could do go through life and all you could do is move that on your hand, could you accomplish anything? Couple things, right? Okay. But when I go to pick up this coffee mug, I'm using 2 or 3 or 10 different ninja moves, right? To pick this thing up and ultimately solve the problem of moving this cup around. Okay. So I like to think about a CPU as this collection of magic tricks, collection of little tiny abilities. So call this a collection of magic tricks where none of them are all that impressive on their own, but when put together in sequence, can solve interesting problems. All right, so we kind of talked about this last time with our old computers that used to be the size of a gymnasium, and you would turn things on and off with little light bulb things, these vacuum tubes. That was our way of controlling values. And we'll be talking about binary and hexadecimal and things like that here pretty quickly. But effectively, when you were turning the light bulbs on and off, you were setting zeros or ones, whatever that ends up meaning for how computing works. All right. Now, the invention of the transistor is what replaced that idea of turning light bulbs on and off. Now we have this thing that's just a digital switch, turns on and off. Okay. And then we got better and better and better at shrinking those things down to the point where we can now fit millions and millions of them onto a little tiny die. In fact, if you ever see a processor is kind of like that big, something like that, most of that's not the processor. Most of that is heat dissipation and stuff. The processor itself is this little tiny die that's on there. It's probably a centimeter squared, something like that. And your modern processor probably has between 4 and 8 of those on there. This is more of an architecture thing, but in any case, if you think about that like a neighborhood or a city, what's built on that is a whole bunch of little magic tricks. And a magic trick is going to be things that the computer might do. That is, move some memory from one place to another place. So inside of our computer, we have memory that's storing stuff. We have our system memory. So that's the thing where you have like 16 gigabytes of RAM or 32 gigabytes of RAM, 8 gigabytes of RAM, whatever. But then when you get close to the CPU, you have register memory, which is really, 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 really fast, but much smaller than 16 gigabytes of memory. It's usually their 32-bit registers or something like that, or 64-bit registers. Now, a bit is, I think did we cover that a little bit last time? Did we talk about bits and bytes and all that jazz? We at least did the math with it. I remember dividing stuff to give you 0.0008 gigabytes or something like that. So let's just create that slide real quick. Call this guy bits and bytes. I need 2 of these dudes. All right. Anybody tell me what a bit is?
Like a binary.
0, 1. All right. What's a byte? 8 of those. All right. So we look at these as 2 different columns. To get from the first column to the second one, we multiply by 8. To get from the second one back to the first one, you divide by 8. All right. So you're going to be able to do any of this stuff by just doing two moves: multiplying or dividing by 8 and multiplying or dividing by 1024. All right. So let's stick over with the byte side of things, since that's usually what we'll say out loud, and then we'll talk about the internet scam. All right. So after bytes, we get kilobytes, big B. So a kilobyte is 1024 bytes, not 1,000. Specifically 1024. 1024 is a power of 2. To find computers, we use a lot of powers of 2. All right. After that, megabytes. That's 1024 kilobytes. Gigabyte, 1024 megabytes. Terabyte, 1024 gigabytes. You can keep going. You can do petabytes, exabytes.
That's what a terabyte is. It's not like just.
A terabyte is 1024 times 1024. That's gigabytes. Times 1024. That's kilobytes. Or sorry, megabytes. Times 1024. That's kilobytes. Times 1024, that's bytes. Times 8 is bits. So 1 terabyte hard drive stores this many zeros and ones. Let's see, that's thousands, millions, billions, trillions, quadrillions. So 91 quadrillion, 690 trillion, 473 billion, 663 million, 496,192 unique zeros and ones makes up a terabyte. All right, so when you get a 1 terabyte hard drive, when you store all that stuff in it, that's made up of zeros and ones. That's the building block of computer data. All right, that'll make more sense as we go through it. All right, so over here on the bit side, we have kilobit, small b. This is 1024 bits. Megabit, small b, that's 1024 kilobits. Gigabit, Small b, that's 1,024 megabits. Terabit, even though nobody really says that, is 1,024 gigabits. All right, so everything you need to know about storage size, data transfer speeds is contained in that one slide. If we fast forward 20 years, it'll still be contained on this slide, but we might have to add petabytes or exabytes and 2 more columns. And if we went to a petabyte here, PB, that's 1,024 terabytes. So on and so forth. Then you just got to find the math name for the next ones. All right. So now let's talk about the, as you noticed, I kind of bounce all over the place. So it's kind of makes it fun and interesting, I suppose. Let's call this the cable modem scam. How many of you have internet at home? Either a cable modem or DSL? How many of you have cable modems? How many of you don't know what I'm talking about? Let's go there. All right, so how many of you get your internet from the cable company? Spectrum, Comcast, something like that? All right, how many of you get your internet from the telephone company? AT&T, Verizon, T-Mobile, something like that? Okay, those would usually be DSL, or the newfangled thing is they sell you the little boxes that let you use their 5G cellular network to give you internet at your house. The scam is all of them are doing it. All right. How fast is their internet at home? Do anybody know how fast their internet is? When you bought internet, I realize maybe your parents are paying for it or something, so you didn't see the bill. Anybody have a guess how fast your internet is? 1,000 what? All right, so 1,000 something. What do we got? Oh, 600 what? You're avoiding those things. Gigabytes? We have 600 gigabytes down. Pooh, man. If only. All right. The baseline internet that most people would get today, they've upped it over the last year. It might be 400 now, but it was for a long time, it was 200. But let's just use 400. It's 400 megabits, small b, per second. Now, when you watch the commercials, they all say, oh, it's 400 meg internet, or 1,000 meg internet, or a gigabit internet. You know, the new cool thing is 1 or 2 gigabits per second. So 400 megabits per second is actually 400 divided by 8. That's 50 megabytes per second. We jumped from this column to this column to get us to the bytes. Because when you think about file sizes, when you download things off the internet, you're usually seeing them in bytes or gigabytes for the size of the thing you're downloading, right? Yet your internet speed is in bits, because bits sounds bigger than bytes. Doesn't it sound more impressive if you go and buy 400 megabit internet versus 50 megabytes per second internet, even though those two things mean the identical thing? Make sense? 1 gigabit per second internet is 1,024 megabits per second internet, which is 1,024 divided by 8 would be 128. So 128 megabytes per second. So if you have gigabit internet at your house, which is, let's just call that the fastest internet you could buy. A couple places have 1.5 or 2 gigabit or whatever, but 1 gigabit, we'll just call that the fastest internet you can buy. How many of you are gamers? Okay, when you download the latest, greatest patch to your favorite game, how big's the file? Many gigabytes. Give me an estimate. 120 gigabytes. All right, so if we just downloaded, download update to what, Call of Duty? So let's say this is roughly 120 gigabytes. How long does that take to download on your internet connection theoretically? Okay. Okay, well, let's do the math. Right? You know, like, how many of you seen the show Big Bang Theory? It's like, is that a rhetorical question? Or would you like to do the math? Good episode. All right, so let's see. We have 120 gigabytes of total data that we need to download. And we have a 400 megabit per second internet connection. Well, let's find out how many gigabytes per second 400 megabits is. All right, so right off the bat, we're at 50 megabytes because we did that conversion up here. Then we take our 50 and we divide it by 1024. So that's 0.05 gigabytes per second. It's rounded, keep the number easy. All right. So really, this internet up here has the theoretical possibility of 0.05 gigabytes per second of download. So every single second we can bring down 0.05 gigabytes. 120 divided by 0.05 is 2,400 seconds. 2,400 seconds at 400 megabits per second. All right, now we know how to do the conversion from seconds to stuff. So we have 2,400 divided by 60. That's the number of minutes. 40 minutes. Theoretical maximum. Okay. Now, so call this about 40 minutes. Now, how many of you feel like on your home-based internet, and keep in mind, this is kind of baseline internet. We're not talking about the fastest. Let's call it middle of the road. How many people think you could download the 120 gigabytes in 40 minutes? Or is it usually longer than that? Why? Why is it longer? Why? We're paying for it. You call up the cable company or whatever and say, hey, I'm paying you for 400 megabits per second, 400 megasecond, or maybe we just say gigabytes or some number, right? I'm paying you for all this money. I'm not getting it. I'm paying you for all this speed. Why aren't we getting it? Okay, so that's one thing inside your house. You're sharing, you can think of your internet as kind of like the water source coming to your house. And if somebody is taking a shower and running all the sinks and all this stuff all at the same time, water pressure can start dropping off, right? Okay, we have a maximum of 400 megabits per second that can flow to all the internet devices in our house. Now, let's assume, like most gamers, you're doing your patch at 2 in the morning. Everybody else is asleep. Nobody's streaming Netflix, whatever, blah, blah, blah. So now why aren't you getting your full internet speed if nobody's sharing it with you except maybe Alexa or something like that, using a little bit. Okay, so why aren't you getting your full speed then? Again, you're paying for it. Go ahead. Oh, well, potentially how far the servers are, but you can only download as fast as whoever you're getting it from can upload it to you, right? Your download is their upload. Now, something he mentioned was that, he had some number of, I think you said gigabytes, but like we could throw it 200 years in the future. Well, actually, probably 40 years in the future, you're probably being gigabytes. But, there is a different speed of upload and download. So at your house, your download speed will be higher than your upload speed. It's called asynchronous internet. So a lot of times you might have 400 megabits per second down and maybe something like 60 megabits up. Something like that. Much, much, much slower. Why? Why is it slower going up? Just because? Ripping you off? You can get synchronous internet if you go and get business internet. Usually it's the same speed up and down, but asynchronous is what 99.99% of consumers have. What do you think? Okay, well, we certainly are, right? So, I mean, most of you, when you're using the internet, you're digesting stuff from the internet, right? You're surfing the web, you're downloading a big patch to the game, checking your email, which brings data here. Now, when you search the web and you type in, www.google.com, for example, you're sending this little tiny message out. That's your upload, saying, "Give me the site for google.com." And then your fast download rips it down, right? Now, is that the only reason? They're just like, oh, you don't need all that upload, so we're just not going to give it to you. Maybe it's true. They happen to know that you're going to spend a lot more time downloading than you are uploading. So why should they sell you faster upload? But there's actually another reason. What do they not want you doing at home if they can avoid it? They don't want you running servers. If you had a computer at home and you were serving stuff to other people, they want to limit how fast you can download or how fast you can upload because your upload is somebody else's download, right? You could be, running a video game pirate website out of your basement where you have terabytes of data that you've given access to the entire world, and they're all coming and trying to download off of your internet connection. And let's call it 200,000 people simultaneously, because you're popular, right? 200,000 people simultaneously are sharing your 60 megabits per second upload. Man, that thing's going to be a crawl, right? Okay, so one of the reasons that we don't necessarily always get our maximum download speed is because we can only go as fast as whoever is serving it to us. Now, that doesn't mean that half these sites you're going to are being served out of, somebody's home internet. That's not likely the case. But not all companies are created equal. Who do you think has higher bandwidth internet? Google or Bob's software company? The one with the deeper pockets, probably, right? So Google, you're probably going to get pretty close to your maximum internet connection unless it's super busy, right? But now we've also adapted because Microsoft, obviously, probably has really fast internet, right? Okay. Now, how many people in here are Windows users, either on your laptop or on your gaming machine at home? Most people, right? All right. So when there's a new update to Windows, maybe the update is, let's just say, a gigabyte download, or yeah, let's just use a gigabyte as the example. All right, so it's a gigabyte download for the latest software update. Now, how many people around the world are running Windows at any point in time? Round down and say a ton, right? A lot of people. They're all trying to download 1 gigabyte of data all at the same time. Even Microsoft's internet could be drugged to the ground, right? That's a lot of people all asking for the same data at the same time. So what was the early solution to that problem? Depending on how long you've been patching things, this becomes less and less relevant as the, students weren't around like when this was a thing. In the early days, what did they do? They tried to stagger the release. You only got the pop-up on your screen. You still see this sometimes on your smartphones where one of your friends says they updated to iOS whatever, but you haven't gotten the pop-up on your phone yet. Because they're releasing it to 1,000 people at a time every 20 minutes or something like that. That way they're trying to control. It's kind of like those lights when you're getting on and off the interstate or on the interstate, trying to control how many people are getting on at once. So that's one approach. Another approach, how many of you have heard of BitTorrent? Okay. And you use it for perfectly legitimate reasons, I assume, right? Everybody? BitTorrent. What is BitTorrent? Go ahead. Well, okay. So maybe you walked right into that. It actually isn't pirating software. It just happens to be used for that pretty often, but you never use it for that. Yeah, you would never do that, of course. How how does the technology behind BitTorrent roughly work? I'm not looking for an exact description, but how does BitTorrent, what does it roughly do? Go ahead.
Someone like uploads something and then you can download it from BitTorrent.
So, but BitTorrent isn't the server. BitTorrent is the community organizer. So if all of us in here wanted to download the Call of Duty patch or the Microsoft Windows patch, and Microsoft put it up on BitTorrent, use that tech. So BitTorrent's a technology, not necessarily a company. All right. So they put it up on a BitTorrent technology. What would happen is the first several people who are downloading it would be downloading it right from the horse's mouth, right from Microsoft. But now, as they start collecting those bits, because we said a terabyte hard drive has those zillions of bits in it, right? At the end of the day, whenever we're talking about computing stuff, we're talking about bits, zeros and ones. And that'll make sense to you later on. Hopefully it's starting to kind of make a little bit of sense now, but we're going to be doing all sorts of stuff where you'll see this. All right. So as soon as the first couple people start collecting enough bits that they can start sharing those bits with other people. Now, maybe when you go and start getting your software update, you're not pulling it right from Windows, right from Microsoft. You're pulling it from somebody else who said, oh yeah, I have the first 1,000 bits. And then it creates this web of monsters, right? So now what you've done is you've built the ultimate internet connection, an interweb where, not that many people are sharing Microsoft's only upload server at once. Instead, you're all downloading from each other. You're getting some of the bits from him and some of the bits from him and so on and so forth. That's BitTorrent. Okay, now, it happened to be used for pirating software. Why? Even though you never used it for that, obviously. I've heard that it's super easy to just click the button and stuff just starts downloading. It's not just software, it's movies too. Uh, but why? Why did people start using it for that? Well, first of all, as individuals, consumers, we probably didn't have a whole lot of stuff we actually wanted to share with other people. But if you were one of those folks that took the video camera into the movies, and you got the cam, and then you uploaded it there, or you downloaded a video game and applied the crack to it or whatever, and put it up there, why would you choose to use BitTorrent rather than just run a server out of your house? Could be you could protect it from a server coming out of your house. We already gave the answer today once. What's the problem with running a server out of your house? Limited upload, right? So if you're sharing your cam with the rest of the world, it's not going to take that many people downloading just from your computer in order to maximize your upload speed. But if you put it out there across BitTorrent, as soon as a couple people start getting some of your file, they could start sharing with other people. So now you've taken a whole bunch of 60 megabit per second upload speeds, and you've turned it into a gigantic download speed opportunity. Make some sense? That's what BitTorrent is. It solved a problem. Okay. Today, most of your software updates, when you go to Call of Duty or whatever, most of those things are being distributed through a technology like BitTorrent. Okay? You are not downloading directly from the source. You're downloading from the community of people that are downloading. All right. So realistically, you should get pretty close to the maximum possible speed of the Call of Duty update. Why don't you? Just out of curiosity, how many people in here are Call of Duty fans? Play the game a lot? Do we have a better video game that everybody plays that has software updates? I'm not talking like Hello Kitty or something, like something with legitimate software updates. Go ahead. Okay. All right. So Destiny, first-person shooter, right? Another, science-y first-person shooter / MMO, but that never made sense. All right. If you're a big fan of the game, and a new software just released. Are you probably one of the first group of people who are going to try to patch it? You're going to download it early on, right? Before the bits have saturated the internet for downloading from a whole bunch of different sources. So you're limited by the more people who already have the files, the better chance you have at maximizing your internet connection. Make some sense? So if you go and download it 2 weeks later, after everybody already has it, I think you'll notice you probably get pretty close to your maximum internet speed so far as what you have available after sharing with all the other people in your household who are now watching, streaming stuff or whatever.
So if no one's downloaded it yet, your internet connection is gonna run slower compared to if you have the 20 people, like in front of you who already downloaded.
Yeah, if you're the very first person who's downloading it, you would be starting to get it from the makers of it. So Blizzard Activision for they make Destiny, right? Blizzard Activision makes Destiny.
Bungie, yeah.
Oh, Bungie. Oh no, that's Blizzard Activision. They own it, don't
Yeah,
they? They bought everything. Yeah, they're the Walmart. All right, so if you were the very first person in line, you will be limited by however fast they can put it out to you. And keep in mind that there could be a difference between what they technologically are capable of putting it out to you and what they've throttled it to make sure that internally at their place, they can still have good quality bandwidth. So they might say, yeah, we can put it out at 100 gigabytes a second, but we're going to limit it to 1 gigabyte a second across everybody who's downloading from me at once. Go ahead. Probably, well, they're not really reaching into your device. They don't have like access to everything in your device. Really, it's your device has said, I am participating in this torrent. So when you download a torrent, it's a .torrent file. And that file is not very big. You're basically adding yourself to the IP address of people who have files to give, and but only for that data source, not for all your data sources. So it's only for that one, But real, I'm just going to make a guess here. Let's see what kind of BitTorrent user he is. Are you one of them that downloads and as soon as you have the whole thing, you turn it off so you're not uploading to other people? Oh, you share.
Yeah.
See? Nice guy. So, I was one of the other ones. Not wasting bandwidth on other people. Once I have it, done. I never downloaded anything illegal though. All right. So we get this whole cable modem flippy dealy. This really had nothing to do with cable modems. We just used it as a real life example. But when we talk about data, whether it's size or whether it's speed, we have to pay attention to the rate we're going. And this isn't new to us. We deal with this in real life. If we're here in the United States and you're driving down the interstate and you see that the speed limit is 70 miles per hour, that is different than if you were over in Europe and you saw a sign for kilometers per hour, right? They means there is an equivalent kilometers per hour to 70 miles per hour, but they do not mean the same thing. We could map between them. Same things here. Make sense? Good.
If someone were to be downloading something,
Theoretically, hypothetically, all right?
What percentage wise does like a VPN actually protect you, like from getting a suspicious letter?
What?
He's basically saying, if I steal somehow the internet, how can I make sure they don't know it's me? That's the question he's asking.
I were to do it, I would do one, but my friend did it and he got a cease and desist letter.
All right, so and this, I mean, so really it's actually a good question based on what we're talking about here. Because one thing that we'll see with technology is almost everything we're asking computers to do are things that are problems that we have figured out how to solve ourselves, but don't want to waste our time doing it. So we've trained this thing to do it for us. All right, so it's just really, really, really fast at doing simple things. Most of our technology stuff is not doing anything that incredibly complicated behind the scenes. It's just doing it really, really, really fast. So He's talking about a VPN, virtual private network. So you got to start off with abstracting it away. Don't think about what you could potentially use a VPN for. Ask yourself, what does a VPN actually do? A VPN masks your IP address. So your computer has a phone number on the internet, a unique number called an IP address. We're not going to go too far into networking here, but somewhere along the lines, there is a public IP address that your computer does have. You might see numbers on it like 10.0.0.123, or you might say 192.168.1. How many of you have the 192s at your house? Who has the 10s at their house? That's pretty common, the 10 one. So it would be entirely possible for you to have 192.168.232.7 and somebody else to have that identical IP address inside their house. Those are non-routable IP addresses. They're unique within your little network. All right. But every single computer that's connected to the internet that can go to google.com, at some level, it's masked potentially several times. There is a public IP address. Maybe it's a router somewhere that is asking for Google on your behalf. The router has a real IP address. It sees that, okay, this person with this 192 whatever is connected to me. I'm going to ask for it on his behalf, and then I'll ship it over to the final destination. All right. The who? What? Oh, thank you. All right. So anyways, what's a VPN do? It masks your IP address to make it look like you are from a different place. So when you launch your VPN, the legitimate uses of VPN are privacy uses. So you might say, look, I'm at work, or I'm doing stuff here that if I'm in a coffee shop and people are possibly sniffing network packets or something like that, I kind of want to be protected. So you would use a VPN, which gives you a IP address somewhere else in the, it'll probably default to whatever the fastest connection is. So you'd probably be somewhere in the United States if you were doing this for, let's call it, legitimate reasons. But then it'll encrypt all the data for you automatically. So you're protected, and you just happen to be getting a different IP address. So it's kind of like they really can't find out who you are because you're using an IP address that isn't your real IP address. It's somebody else's IP address by which you're making all your requests. But your data is also encrypted. So a VPN kind of helps you on two fronts. One front is they can't find where you live. The other front is a lot of the anti-piracy software out there looks for patterns in the actual data. So, for instance, torrents are very easy to tell the type of data it is. So they can actually get the exact name of the movie or software you're downloading, as I'm guessing your buddy found out. Yeah. they when he got the cease and desist, they gave him the list of things that he's downloaded. Whereas a VPN, at the very least, that would be hidden because it would just be random encrypted stuff. So let's call that the legitimate use of a VPN. So at the end of the day, if you were to use a VPN from your house, you would look least, my guess is when you use a VPN, you're probably picking some foreign country, right? Or your buddy has picked a foreign country. Oh, that's true. Because another use for VPNs is if you want to watch Australian Netflix, you can switch your VPN to use the source being Sydney, Australia. And now all of a sudden, when you launch Netflix, you're looking at the library from Australia. It's great. So that might be one reason to use another country. But otherwise, if you were, not that any of you would ever do this, but if you were pirating software or stealing movies or whatever, I would think you would look least suspicious using an IP address from the United States, but just not your IP address. Because if you're a company and somebody's distributing software or downloading software from stuff, are you going to look more suspicious if it's some random IP from the Czech Republic, or are you going to look better if it's just from Austin, Texas? It's some grandma on the internet from Austin, Texas downloading this, right? So that's your VPN and all right. Other questions about that stuff? All right. So speed stuff. Let's see. So we talked about bits and bytes. Now we've seen an application of these bits and bytes. We've talked about CPUs. What's a CPU? It's this collection of magic tricks. Nothing that our CPU can do. If we were to look at our CPU through a microscope and we saw each little magic trick on there, it's implemented in terms of wires and these logic gates. We have AND gates and XOR gates and OR gates and all sorts of things like that. Then they have these specialty chips that are they do 3 or 4 things, because maybe it's 3 or 4 things that are always getting done, in sequence. So for instance, maybe on a daily basis, human beings pick up cups often. That's a move that we tend to do. So in our brain, they've probably created a little subroutine that is the 5 or 6 magic tricks that string together to grab, right? And they've turned that into a single magic trick, even though it's just several things strung together. Go ahead.
Processes and then turn them into actual outcomes.
That's what a CPU has. A CPU has this ability to do stuff. So we're like the CPU. We have all this potential. I can potentially reach out and grab this cup, but something had to tell me to do it, right? So that's our little voice in their head saying, "Oh, I want coffee," right? So, but the CPU itself has the ability to do all these things, but somebody has to ask for it. When we're talking about a computer here, who's telling our computer what to do? We are. And as super users, we're writing computer programs that specifically tell this guy what to do. We're not having to go through Microsoft Word being only limited to the features, the abilities Word gave us, or whatever software we're using. We can write our own software to do whatever we want. That's the power, the superpower of coding, right? But ultimately, at the end of the day, we need to tell this guy what to do. And what's ultimately happening, after all the little hoops that might happen between what a human being is capable of writing, we said last time, we don't want the little 2-button keyboard where we're just tapping out zeros and ones all day long. It's not compatible with people, right? So we want to type something that, fine, if you're not a coder, you haven't seen it before, to most people, when they see code, it looks like gibberish to them. Just like when I see Cyrillic characters when somebody's writing something in Russian, just like, what is that? Right? But there are plenty of people who speak that language and that's perfectly easy for them to read, right? Okay, so it's kind of the same thing. A person who's not a programmer doesn't have the vocabulary to understand what's happening on there. They just see symbols and stuff and assume it's difficult. Go ahead.
Which one do you put the thermal paste on? Is it the GPU
or CPU? When you buy a GPU, the almost always the fans are already on it. Thermal paste sits between the physical CPU and the giant fan that goes into, the heat sink and fan that goes on top of it. It just helps dissipate the heat evenly across the metal plate. If you didn't put it on there, you'd probably be fine. Nowadays, back historically, the materials of those things didn't distribute as well, so maybe the paste would have been helpful. All right, so we got a decent idea of what a CPU is. It has all this potential, just like any of us. If I say grab this coffee mug, that's a little computer program that tells me to go get the coffee mug, bring it up here, open the lid, drink it. That's a CPU doing a bunch of magic tricks in a row to accomplish something. Make some sense? All right. That's what a CPU actually is. Last time we wrote this slide, low level, high level machine language. All right, so we've already kind of talked about most of this. So machine language, That's the zeros and ones. When all is said and done, after we peel away the graphics and all this other crap, this guy speaks zeros and ones. And every one of us in here, by the end of this course, are going to also be able to speak zeros and ones. Now, first of all, I'm making your future courses easier. So what we're talking about right now is effectively computer architecture stuff. You cannot be a computer programmer at a professional level without understanding how this thing works. Even though when you're out in the real world, you're actually out there writing software, whatever, you won't actually have to understand how this thing works 99% of the time. We're preparing for that 1% of the time when you're the only one on the team who can solve the problem because you understood what was happening under the hood. Make some sense? Otherwise, you're only as good as the tools you have available to you. Some people are great problem solvers if you give them Photoshop to wield. They can do all sorts of stuff with Photoshop. But as soon as they have to get outside of Photoshop, they basically can't even use a computer. Kind of know what I'm talking about? So we need to be the experts at this stuff. So, but we are humble enough as human beings to admit that machine language is going to be rough. Okay, we are going to be very error prone, popping out zeros and ones. So now we talk about low-level languages. So low level and high level, let's call that the two programming language types that are compatible with people. High level being the one we really want. We're getting there. That's the power screwdriver, right? The high level languages. But let's look at a low level language. Low level has a one-to-one relationship with the CPU. Now we know what a CPU is, right? So every instruction in a low-level language equals exactly one magic trick on the CPU. So if you were to tell me you were to write that program in assembly language for me to pick up that cup of coffee, there would be several different magic tricks you're going to have to individually tell me in order to accomplish that task. Now, we could probably do it as a human being. We knew we had this list of magic tricks in front of it. Okay, these are the things the human arm can do, the arm and the hand or whatever, right? So if you are given that list, you study it a little bit, you probably can come up with a sequence that would let you pick up that cup, even if it was a little janky, right? You know, you might not be able to use their hands, so you pick it up like this or something like that, but you'd be able to pull it off one way or another. So let's look at some low-level code. So this is assembly code. This is Hello World, the proverbial first program that you might look at in a that you typically write in any programming classes, the Hello World program that just spits Hello World out to the screen. All right, this is Hello World in assembly. Now let me show you Hello World here in Python. There's Hello World in Python. One line of code. Python's a high-level language. If we were writing this in Java, be more than one line of code because you have to have like a structure to your Java program. But really, at the end of the day, the thing that actually prints Hello World out is system.out.println Hello World. If you were in C++, the thing that actually prints it out is cout Hello World. Console that write line, Hello World, is C#. Printf Hello World is C. All the same crap. All right, these are high-level languages. But what we're looking at right here is a low-level language of Hello World for Linux. Now, there's a kicker in there. Operating systems. What's an operating system? Okay, so Windows, Mac OS, those would be examples. I mean, short answer is you're right. Longer answer is technically those are distributions. The operating system that's under the hood of Windows is called the NT kernel, Windows NT. The Operating systems that's under the hood on Mac OS is OpenBSD Unix. It's a Unix kernel. If you run Linux, Ubuntu, or something like that, at the core, the operating system is the Linux kernel. But typically when we think about operating systems, we're thinking about distributions because we're not just talking about the operating system. We also assume that there's going to be like a text editor of some kind or a built-in web browser and that stuff. So the distributions kind of give us the starting point for using the operating system. All right, but an operating system is a layer. Oh, drop some keys there. Is a layer that sits between the user and the hardware. And we already said that we don't want to have to type out zeros and ones. We certainly don't want to have to sit here with metal pokers trying to connect two ends of circuits together and stuff like that. You know, we go back to those old days when they were physically turning on the vacuum tubes. Operating systems make our life easier. We can use these things more easily with an operating system. But now, operating systems provide a series of system calls that let us do common OS things or common computer things. Let's say that. As an example, do you think on a computer it is common that stuff will need to get printed onto the screen? Very common, right? So we got this monitor thing. It's going to be very common for us to expect the operating system to be able to make stuff show up on that screen so we can read it. Otherwise, we have no idea of what's going on, right? So built into every single operating system, we have this power tool called syswrite or similar. That is a gigantic program, probably, call it hundreds of lines of code, that knows how to talk to your graphics card, your GPU, which knows how to talk to your monitor, the frame buffer, does all these things, and ultimately you could just say, print hello world, and it magically happens after all this crap behind the scenes occurs that you didn't even see. All right? This is the entire hello world program. We're using power tools here. Hello world in reality, if we were not using the power tools the operating system gives us, would probably be several hundred lines of code. So let's see how this is working. And what you're going to see is how computers actually work with their low-level languages, the assembly code. Everything is kind of a staging process. We kind of like set the table up, and then we say, okay, I got everything right where I want it. Operating system, go. So let's see what happens here. So we see, so I mentioned a few minutes ago, we have different kinds of memory, right? You got your system memory, that's your 8, your 16, your 32 gigs of RAM in your computer. You have hard drive, that's your 1, 2 terabyte of stuff. Hard drives are slower than system memory. System memory is slower than cache memory, L1, L2, L3 cache. And L1, L2, L3 cache is slower than register memory. Basically, the closer you are to the heart of the CPU, the faster the memory is and the smaller the memory is. All right. So what we're seeing here, this RAX, RDI, RSI, these are how we talk to individual little register memories on the CPU. Tiny, 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 32-bit memory locations. All right. So here's the most popular, let's say, assembly language command is move. This says move the number 1 into this memory location. Okay, so I've moved 1 into that memory location. Let's think about this like we're setting the table. So I put a 1 right here. Then we're moving another 1, seemingly for no good reason, into another memory location and put that 1 there. All right, and I'm going to tell you about these in a second. Then we move whatever this MSG thing is into this other memory location. This will be a pointer. Then we move something else into this memory location. So we are putting 4 things. We're setting the table with 4 things. Nothing has actually happened yet, computing-wise. all we've done is say, okay, we're going to these four things set up. All right, everything's the way I want it. Then we call upon the operating system, syscall, to take over from there. So now in Linux, when we say syscall, when we say Linux, you go ahead and take it from here. I've told you everything you need to know in order to solve this problem. Write something to the screen. What did we need to know? What does syswrite need to know? It needs to know, well, what does the OS need to know to call syswrite? Well, it needs to know the system call that we want to use. Syswrite is equal to system call 1. That guy right there. The reason we put a 1 there is because somewhere in the documentation for the Linux operating system, it lists the system calls that the operating system supports. And right at the top of the list, you have something called write or syswrite or similar. And next to it says, yeah, this guy's called number 1. Okay. At the end of the day, computers like numbers. We like words. These guys like numbers. That's why you're always going to see things ultimately get associated with numbers. All right. So we're going to say, okay, I want to write something that happens to be number 1. All right. What else does it need to know? Where do I want to write it? So what are my choices? If you're writing something, you might want to write it to the screen. You might want to write it to a file. You might want to write it over a network connection to send it over the internet, something like that. So there's different destinations that we want to write something to. In this case, we want to write it to the screen. This is standard output, which is also a 1. So standard output is the monitor. All right, that's that one. What am I doing? Where am I doing it? Where am I? So I'm writing it to standard output. Then what am I writing? Down here, we have this section for data. Now, last time we talked about how do human beings solve problems? Memory, asking questions, repetition. Memory is usually done through something called variables in programming languages. So what we've done here is we have associated a variable name, MSG, which stands for message in this case. We could have called that cat. There's nothing special about MSG here. Okay? And we've set it equal to hello world. Actually, what it equals, you see how this guy has a DB before it? We talked last time about loosely typed and strongly typed languages. Now keep in mind, we throw all sorts of stuff out, so I'm not expecting you to memorize all this. Hopefully you're starting to see things just sort of float together and you're seeing all these things are related. Okay, so a data byte, we already know what bytes are. We learned that today, right? Okay. A data byte, what MSG holds is actually just the H. But it doesn't actually hold the H. It holds the location of the H in memory. All right. So what we're really saying here is, what am I writing? We're saying, where does the string I am writing start in memory? Where's the beginning of it? All right. And then the last thing, so we're putting into RSI the pointer. This is called a pointer. Pointers are memory addresses. So RSI is, we're pointing to the H. This is where H is in memory. What's this last thing? It's the length of it. How many characters are we writing? Those are the four things we need. Or if you want to think about it, sys_write requires 3 inputs. Where am I writing? Where does it start? How long is it? Why do we need to know how long it is? Because if I only know about the H, I need to know if I keep taking steps through memory, how many steps do I need to take to get the entire sentence or whatever that you want to print out to the screen written? All right. So we're saying I want to write something out to the screen. I want to write it starting with my H here. And I want to keep going for, what is this? 5, 6, 7, 8, 9, 10, 11, 12. And then technically this is a carriage return, so 13. So this guy will boil down to the number 13. I'm going to write 13 things to the screen, starting with the location of this guy. How is hello world? That's from the exact example here. Stored. I mentioned a few minutes ago that computers like numbers, not letters. We like letters. So how is an H actually stored? How is a lowercase e, uppercase L, or lowercase L, whatever? Anybody know? Probably type something in. Good. Thinking of something else, but basically any of these words will be related to each other because yeah, so let's say no, it's not binary, even though it could be. Binary and hexadecimal are basically the same thing. We can write the number 101110 in binary, we can write that in hexadecimal. And it means the same thing. Just like miles per hour versus kilometers per hour, we can convert between those things. And we'll talk about those things. But okay, so we have old school. We have something called ASCII, American Standard Code for Information Interchange. New school, we have Unicode. All right. Now let me show you what this is. So let's just do ASCII table. This is readable enough. Let's go find our H. Here's our H right here. H is decimal 72, which is the same thing as hexadecimal 48, which is the same thing as octal 110, which is the same thing. Well, this is the HTML code for it. They would be a binary equivalent to this if we wanted to, but and we'll talk about how to convert between these later. So don't worry about that. Just know that 72, 48, and 110 all mean the same thing in different bases. This is in base 10. This is in base 16. This is in base 8. And we could write it in base 2 if we wanted to. And we'll see how that works. But at the end of the day, notice here that there's a letter H here. And if we want to just live in decimal world for right now, since that's where humans are comfortable, right? 10 fingers, 10 toes. We like the 1 through 10 stuff. We are looking at the number 72 maps to an H. Here, I'll just add another code block. Nope, doesn't like me converting that to yeah, I'm not going to screw with it. Doesn't like me converting. Oh, because it probably wants Unicode, but whatever. It maps to an H. That'll be a 72. All right. So when we look at this word hello, what it's actually storing is the number that references on the ASCII character table or the Unicode character table. ASCII is 8 bits. It's actually 7 bits, but let's just say 8. So that means that there are 256 unique characters on the ASCII table because we only have 8 bits to work with. How did I get 256? If ASCII is 8 bits, which is the same thing as 1 byte, right? And Unicode is 16 bits, which is actually 2 bytes. 16 divided by 8 is 2 bytes. All right. How is the word hello actually written? Well, we saw that the H is a 72. Let's go and find our lowercase e. Notice that all the uppercase characters are right next to each other. A is 65, B is 66, C is 67. It's important that they're right next to each other. So if I have a character that's equal to A and I add 1 to it, now it's a B. A plus 1 is actually a B because under the hood, they're stored as numbers. And we'll see examples of that. But I'm looking for our E. E is the number 101. Then we have 2 L's, 108. And then we have an O, 111. All right. So the string hello, like that with a capital H, is actually stored as a sequence of characters, sequence of numbers. 72, 101, 108, 108, 111. Now those are written in decimal. We could write them in binary. Well, if we wanted to. Computers want them in binary, so ultimately it's going to be in binary. So if we're going to write that, how do I take the number 72 and convert it to binary? We have 2 patterns when we're converting between numbers. Number conversions for bases. We'll talk about why we have different bases kind of at the end of this lecture, so probably ends up being on Tuesday. But our common computer bases, binary, base 2, on or off, computers like that. Decimal, base 10, we like that. Octal, base 8, there's a good reason for it. I'll talk about it when we get to it. And hexadecimal, base 16, also a good reason. We'll talk about it. All right, but number conversion bases, we have 2 patterns. To convert decimal to any base, we divide, well, let's say it this way. To convert decimal to base n, we divide the decimal number by n over and over until we end up with a remainder of 0. Remember long division from 3rd grade? Almost all of our hard computer science stuff actually is based on long division, modulus arithmetic. So when you had something that was like, for instance, how many times does 7 go into 8? Goes in 1 time with a remainder of 1. How many times does 6 go into 8? Goes into 8 1 time with a remainder of 2. All right, so we're going to keep doing this until we have a remainder of 0. So let me just do it really quickly since we only have a couple minutes left here. So for 72 in decimal, we want to convert it to base 2. So n is 2. We're going to take 72. We're going to divide it by 2. 72 divided by 2 is 36. I'm going to write the 36 right here. 36 times 2 is 72. So that has a remainder of 0. Then we're going to take our 36 and divide it by 2. And that gives us 18. We'll write our 18 right here. 18 times 2 is 36 with a remainder of 0. 18 divided by 2 gives us 9. 9 times 2 is 18 with a remainder of 0. 9 divided by 2. How many times does 2 go into 9? 4 times. 4 times 2 is 8 with a remainder of 1. 4 divided by 2. How many times does 2 go into 4? 2 times. 2 times 2 is 4 with a remainder of 0. How many times does 2 go into 2? 1 time. 1 times 2 is 2 with a remainder of 0. How many times does 2 go into 1? 0 times. 0 times 2 is 0 with a remainder of 1. So the number 72, we read it from bottom up, is 1001000. That is the binary version of a capital H. If you were storing that. Make some sense? All right. So we'll keep going with this on Tuesday. Remember, look at Canvas. The first homework assignment is up there. It has you go into Google Colab, write a thing that says enter, I don't know, enter your name or whatever, and then it prints it out to the screen just to get you using it. And then you submit a link to your Google Colab thing. All right. I will see everybody on Tuesday.
Attendance, right?